Chapter 8 Generic Business Jet GBJ by the element-based design variable approach using the DESVARP box.com. And so we want to minimize the weight of the GBJ and subject to flutter, buckling, manufacturing, and the strength constraint by the element-based design variable approach. So this is the GBJ model, and this is the structure model. The wing skin upper and lower are modeled by sequence 4 with composite plate elements, which has 4 plies. The spar and rib are modeled by the C-shell element, and the T-tail and engine nacelle are modeled by the rigid element, and we have a condemn 2 to represent the non-structural mass and the internal field. So this is the property car of the C-shell element, and this is the property car of the sequence composite elements. The aerodynamic model is a half-span model. The fuselage and the engine nacelle are modeled by body 7, both are cars, and the vertical tail, horizontal tail, and the pylon and the wing are modeled by CL7. On the wing, we have a airfoil and specified by the PA407 car, this will create lift even at a 0 angle tag because it is not a symmetric airfoil, and this lift and moment we call it mean flow, and is defined by the trim variable called thick cam. The GBJ steady unsteady aerodynamic model has a detailed fuselage plus engine nacelle model by the body 7, and body 7 refer to the second match both.com. The fuselage aerodynamic model is developed by 9 segments. Each segment is defined by a second match, so it has 9 segments. Each one refers to a second match. In the first second match, we have 7 actual stations. Along each station, we have 15 points, and the YZ location of the points are defined by the AE card. And also we use the body 7 to model the engine nacelle. The rear engine nacelle has an open inlet, but the aerodynamic model cannot be open. Okay, so in addition, the body aerodynamic boxes cannot be perpendicular to the free stream condition. So to circumvent this modeling constraint, and we add a cone shape patch to cover the open space of the inlet region, and those inlet boxes are assigned to be a flow-through condition, which will allow 100% of the flow penetrate into those inlet panels. And to define this condition, we use P-body 7. So we have a body 7 to model the engine nacelle, and it refers to the P-body 7, and lists out the box ID on this inlet face, and we will allow 100% of the flow to penetrate into those panels. So to attach a lifting surface, a CL7 to a body, so on the fuselage, it's better to create a cut which allows the wing 07 to attach to it. And also each wing, each 07 generate a two-line vortex from the tip and from the root. The tip one is physical, but the root one is not physical. So we have to somehow cancel the line vortex generated from the wing root. To do that, we want to create so-called the vortex carrier through panel. How to do that? In a CL7, you say the root is attached to the body 7 ID of the fuselage. Then if you do so, the pole one will automatically create panels connecting the panel from the wing root to the center line of the fuselage. And in so doing, this line vortex is cancelled out. And we have to do spline because wing, we divide the wing into three, using 3 CL7. So each CL7 we use spline 1, the even plate spline, and which we refer to the list out the wing box ID, and refer to the set 1, which lists out all the structural grid on the wing for spline. And for the control surface, we have to spline separately, and so we use another spline 1 card to do the surface spline for the aileron. And horizontal, we only have one CL7, so we only is one spline 1 card. And for the vertical tail, we have a 4 CL7 to define this vertical tail. So we need a 4 spline card. And for the fuselage, because it is a beam model, so we use a beam spline, which is spline 2 for the fuselage spline. And the engine in the structural model just a point, and which is all the engine mass is attached to the single point. So in this case, we use attached card to do the spline for the engine nacelle. And finally, one should use the plot mode card to verify the spline input. And the structural model of the GBJ, the wing box has 11 space spanwise bay and 5 chorwise segment. The wing box structure extends from the wing root all the way to the fuselage. And because the leading edge and the trailing edge sections are not considered as a load carry structure and are omitted from the weight design, the skin, the rib as a spot are modeled as an isoperimetric quadrilateral element, namely the seashell. And the non-structural mass and the internal field are modeled by the concentrated masses using Condem 2. The structural model of the skin, upper skin and lower skin, contain composite material. So all the elements we separate into different groups, and so element ID for the of the skin for the leading edge and trailing edge are assigned to be 6001. Element ID for the upper and lower skin starting from 2001 and 1001, modeled by the CQUA 4 with a composite material with 4 plies. Element ID for the spar and rib start from 3001 and 4001, and modeled by seashell. and the skin element refers to the pecan car, which define 4 layer of a composite material. The fiber orientation is 0 plus or minus 45 degrees and 90 degrees, and with no bending stiffness. So we say min. And this composite layup is not symmetric, but since we don't have a bending stiffness, and the stacking sequence does not matter, so it does not change the memory stiffness. The initial thickness of each layer is 0.2. The minimum thickness is 0.005 inch, and for the seashell, the initial thickness is 0.2. The minimum thickness is 0.04 inch. And then we have 4 types of constraint. The first is a flutter constraint, and it's defined by the decon flat car with ID 1099, and which said the damping of all modes should be less than 0 at speed less than 13100 inch per second. And the flutter analysis is defined by the flutter car. So in this flutter car, it refers to the fixed MDAN, and fixed MDAN refers to MK error Z car, which is defined the Mach number to be 0.85, and it lists out the reduced frequency because the ASC matrix has been previously created, so we acquire the ASC back, and this the density, and this the mass unit, this is length unit, and because we have a 12 velocity which is less or equal to 13100, and we have a 20 modes. So the total flutter constraint is 20 times 14 equal to 280 constraints. And the trim analysis is at 4G pull up at the 30,000 feet and the Mach number 0.85. So we define a trim, and it refers to the MK error Z car, and the Mach number is 0.85, and this the dynamic pressure, which is 2.2 psi. The pitch, the trim condition is a pitch one. It is pitch, and so the NZ is 1544.4, which is 386 times 4 inch per second square, and we have thick can, which is the mean flow create lift and moment, and we have an angle tag to be free, an elevator to be free. Okay, we didn't talk about how do we define elevator. This elevator is defined by the AE sub Z car, and then in the AA sub Z car we define it refers to a list of a panel ID which belongs to this control surface, and also we call this control surface ELEV. So we have 2 unknown trim variable, and to satisfy a pitch condition, and this pitch condition is NZ equal to 4G and Q dot equals 0. And executive solution control package. And first, we define a signed runtime database, and because this problem is very large, and each runtime database and the maximum size is 2 gigabyte because this is a 32-bit system. So we want to create 4 runtime database. So by specifying this DLOC. And each one has 2 gigabytes, so we can handle 8 gigabyte problem size. Then we have to say optimize. Maximum iteration is 100. Is the maximum number of iteration. NR fact equal to 0.1, and the default is 3, so we reduce 3 to 0.1, and so because 0.1 times number of a design variable equal to n, so even all constraints are satisfied, at least n constraint evaluations still are to be considered by the optimizer. So this is the minimum number of constraints, which is the number of design variable times the NR fact. EPS equal to negative 50 times e to the negative 3. Increase the default value from negative 0.1 to a slightly larger number, so that any constraint is greater than this number will be considered as a retained constraint. So if any additional constraint in addition to n here, those values are greater than EPS will be added into the list of retained constraint. Conversion limit reduced from the default value to 0.5, from 1 to 0.5, and root equal to all, print out the flutter analysis solution at all iterations. Trim, print out the trim solution at all iterations. Buckle equal all, print out the buckling analysis result at all iterations. Decon equal all, print out the constraint value of all at all iterations. GDES equal all, print out the value of DESVARP design variable at all iterations. LDES equal all, print out the thickness of pcon and pshk at all iterations. And strain iteration equal to all equal to 1200. 1200 refers to an element list Bogota car with ID 1200, and so you will print out the strain in those elements. And the displacement equal to all, print out the displacement of all such a grid due to the trim load. Decon equal to active, print out the active constraint at all iterations. Then we have punch iteration equals last. So we want to punch out the optimized structure at last iteration. GDX equals to all. In addition, in this punch file, we will include the solution of a global design variable defined by the DESVARP. Model equal all, print out the optimized structure model, including all your unique pcon car, pshk car of each sequence 4. And then the user can replace the element and property cards in the baseline structure by those in the punch file to establish a new ASTROS input file. Next, the boundary. In the boundary, we say MPC equal to 1, which refers to the region element RBE2, RBAR, RBE3 with ID equal to 1, with the set ID equal to 1. And auto SPC equal to ES, turn on the auto SPC. Support equal to 35 refer to a support car with ID 35. In the support car, you define the rigid body modes. Method 1 refer to the eigen car ID equal to 1 to specify the eigen solver for solving the model solution. SPC equal to 1 refers to SPC or SPC1 for the car with a set ID equal to 1 to define the single point constraints. Then SL to perform the static aeroelastic trim analysis. Symmetric indicate the structural boundary condition is symmetric. Trim equal to 600 refers to a trim Bogota car with ID 600. And the strain equal to 4000 refers to the decon FT M car with ID 4000 to define the strain constraint. And decon 1020 refers to a decon bulk car with the ID 1020 to define the buckling constraint. So this is for buckling, this is for strain constraint. And flutter FL count equal to 10 refers to a flutter car with ID 10 to perform the flutter analysis. D count equals 1099 refers to the D count flutter car with ID 1099 to define the flutter constraint. Okay, now we want to define the design variables. Because we have a 130 sigma4 on the upper and lower surface, and each sigma4 has 4 layers. So we want to define each layer, the thickness of each layer of each sigma4 as a design variable. So the total number of design variable is 65 times 8. Okay, 8 is each the upper surface has 65 sigma4. The lower surface has 65 sigma4. Each sigma4 has 4 layers, and then we have upper and lower. So the total number of design variable for the wing skin is 520. So this is the Pickup car, which refers to by all the sigma4, which we define 4 layer. Okay, 0, plus 45, minus 45, and 90 degrees, with initial thickness 0.2 and the minimum thickness 0.005. In the DESVARP, it refers to element list, which lists out the element of the sigma4 is 1001, and with a minimum thickness of 0.025. The initial thickness is 0.5. So the initial thickness is 0.2. The actual thickness is 0.2 times 0.5. So the actual thickness is 0.1. The minimum thickness is 0.25 times 0.2, which is sorry, it's teaming here. It's 0.005. So the total. So we have this is for the first layer, the second layer, this is for first layer, second layer, third layer, and the fourth layer, and so on. So totally we have a 520 design variable. Okay, the baseline structure is 0.2, and the initial thickness in the DESVARP is 0.5. So the true the actual thickness is 0.1. The lower bound is 0.025 times 0.2, which is 0.005. Okay, 0.005 is this number times this number. And for the wing spar, and the minimum the thickness is 0.1. The V in the DESVARP, the V min is 0.5. The initial is 0.6. The actual thickness of the baseline spar is 0.6 times 0.1 equal to 0.06. The actual lower bound is 0.4 times 0.1 is 0.04. So it actually is overwrite this number. So as the rib, so we have a 11 rib and with a C for ID. The V mean is 0.4. V init is 0.6. The actual thickness of the rib is 0.6 times 0.1, so it's 0.06. And the initial one is 0.4 times 0.1, so it's 0.04. The total number of design variable of element base is 520 for the wing skin, 78 for the spar, 65 for the rib. The total number of design variable is 663. And the strain constraint is defined by the DCon FTP, and so does the strain limit, and the PCOM car, the PCOM car refers to the MAC A car, and because the PCOM car with ID 171234 that refers to MAC A car with ID 7, it is only referred to by the 130 sigma for cars for defining the wing upper and lower skin. No strain constraint is applied to the spar and rib. The total strain constraint is 130 times 4, equal to 520 for the 4-layer skin element to define the strain constraint. And the buckling constraint, because we have 130 sigma 4, each sigma 4 is subject to the buckling constraint. Even the bending stiffness is excluded from the PCOM car. The bending stiffness is automatically considered for the buckling constraint. Since the lower eigenvalue of a clamp plate is approximately 1/4 to the power 3, is equal to 0.15. So the constraint value is 0.015625. So we have 130 sigma 4 for the wing skin. So we have 134 buckling constraint. Then we have a manufacturing constraint. It says all layer must be at least 10% of the total thickness. So it defines a lower bound of 10% for the layer 1, layer 2, layer 3, layer 4. It refers to the element list. Okay, sigma for 101 to 1065. Another from 2001 to 2065. So there's a lower, there's an upper skin. So the total number of constraint is manufacturing constraint is 130, which we have 130 sigma 4. We have 4 layers, so it's 520. And during the optimization, first at each iteration, it will print out the design variable move limit equal to 2, and the DESVARP P ID 10101 design variable value is 0.5, which is define the entry V init. And the maximum value 0.025 is defined by the V mean 0.025, and the maximum value 1000 is the default value of the DESVARP P car. Since the design move limit is 2, the default value, the current maximum value is 0.5, which is the V init, divided by 2, the move limit, equal to 0.25. So the minimum move limit is 0.25. The maximum move value is 0.5 times 2 equal to 1. Okay, so it has a lower move limit, it has an upper move limit. And likewise for DESVARP P with ID 40105, the entry V mean equal to 0.15 and the V init 0.6, leading to design variable and the 0.6. The minimum value is 0.015. So the current minimum value is 0.6 divided by 2, which is the design variable move limit equal to equal to 0.3, and the current maximum value is 0.6 times 2 is 1.2. So this the minimum move limit, and this is the maximum move limit. Then the local design variable result triggered by the LDES equal to all in the print solution case control. For sequence for ID 1001 is associated PCOM car defines a 4 composite layer with thickness 0.2 for 4 layers. Since the DESVARP P for a car with ID 101 specifies V init equal to 0.5. Therefore, the thickness is 0.2 times 0.5 equal to the actual thickness is 0.1. T over T mean, and 0.1 divided by 0.05 is 20, and where T mean is 0.2 times 0.025 equal to 0.005, and the minimum equal to T mean is 0.005, and the maximum is 2 times V max is 200, where V max is 1000 is the default upper bound value of the DESVARP P, and likewise, sequence for ID 4105 is associated P shell car for non-composite material. So this is the layer index. If it's metal, the layer index is 0. Specify the initial thickness is 0.1, and the associated the DESVARP P for the car specifies V mean equal to 0.04. So the T mean is 0.1 times 0.4 equal to 0.04, and the V init 0.6. The thickness is 0.06. T divided by T mean equal to 1.5, and the maximum is 0.1 times V max equal to 1000. And now it prints out the trim solution. So it says if first it says the trim ID is 600, and there's the moment center, and the reference area. This is the reference core. This is the Mach number. This is the dynamic pressure, and the trim type is pitch. First, you print out the stability derivatives, and this thickness camber, so which represents CL naught and CM naught. So this is CL naught is a 0.1692 for flexible, and for rigid is 0.1684, and this the flexible pitch moment, which is CM naught, is and which is this number, and for the and this the angle attack. So this is CL alpha, and flexible. This is CM alpha flexible. This is the this is C of elevator per elevator. This is CM per elevator, and so the trim solution said, in order to satisfy 4G pull-up condition with a 0 pitch acceleration, the angle attack need is 7.35 degrees. The elevator we need a negative 10.6 degrees. All above area and force and moment are normalized by the reference core, reference area, and with the reference center, REFX, REFY, and REFZ specified in the LZ car. And then we print out the flutter solution. It's a non-match point in flutter analysis at this Mach number. That this density with a list of the velocities, and then it print. We have a four modes. No, we only print, show the first 4 modes. Actually, we have 20 modes, and then at each velocity, there's a mode 1 damping. This is the frequency. This is reduced frequency, and at each iteration, if you specify plot VG_car, it will give you a file. If you specify the file name in the plot VG_car to be vg.dat, and actually we add an integer. 1 is the first iteration. If 10 means the 10th iteration, then you can plot it. Okay, so you can see the baseline has no flutter problem. This line is the constraint value, meaning all the damping below the 13,000 inch per second must be all negative. So the baseline structure has no flutter problem. And then you print out the displacement due to the trim load, and you will print out the buckling analysis result. This is nx, ny, nxy, and this are generated by the trim loads. And the lambda is the lowest eigen value, and the decon value is the constraint value that must be negative to avoid buckling problem. The length and width are the length width of input from the decon BK car. Then the strain is listed in by this element list of a car. So we list out those elements, and within each layer, and you will print out the fiber distance, the strands in the stress coordinate, in the principal strand, and so on. Then for the first iteration, and it says because RF effect equal to 0.1, and we have a design variable 663. So the minimum retained constraint is 66. At the first iteration, all constraint values are greater than negative 0.05. So there's no additional constraint. And then we list out those 66 constraints, and it seems that all belong to the flutter constraint. And then the CT and CT mean are specified the MP per rank car to alter the default value of CT to 0.001, CT mean 0.005. This is to relax the criterion of active constraint. So we have 66 flutter constraint and 66 active constraint for this boundary condition, and then we look at the converging criteria. The first one is that the move limit is 0.5%, specified by the conversion limit. Okay, and the first one is objective function move limit, and this move limit is 3.1%, which is greater than 0.5%. And the second one is the design variable move limit, and this one is 44%, also is greater than 0.5%. Criterion 3, the largest design variable limit is printed out. At the first iteration, the design variable is DESVARP with this ID, whose percent move limit is 100%. The upper limit of the design variable move is defined by the move limit, the curve, the default value is 2. Apparently, the largest design variable move reaches its upper limit, thereby percent move equal to 100%. Because the criterion 1 and criterion 2 are not satisfied, so it is not a converged solution. And it takes 27 iterations for ASTROS to achieve a converged solution in which 240 retained constraint and constraint value are greater than EPS. 42 active constraint value are within 3 times CT and 2 times CT mean, and the 0 violate constraint are shown in the last iteration. And iteration 14, 15, 17, 18, 19, 20, 23, even the mathematical programming considered the optimization are converged, but the constraint evaluation performed by the optimizer in the subsequent iteration detect that some constraints are slightly violated. Thereby, the iteration continue until 27 iteration. At the 27th iteration, the weight is 120.88 inch. The baseline is 127 inch, so it's a 5.2% of a weight reduction. Okay, let's look at what happened at the 14th iteration. It said converge. Then why the optimization still continue? And at the 14th iteration, and we have 244 active constraint, 7 fiber strength constraint, 27 panel buckling, 47 flutter constraint, 144 lower bound laminate decomposition constraint. This is from DECON. And so the total active constraint is 244. Among this 244, the objective function move limit is 0.0035%. The design variable move limit is 0.1739%. Both are less than 0.5%. The mathematical programming considered the 4th iteration is converged. However, ASTROS continuously perform one additional iteration for constraint evaluation to ensure that all constraints are satisfied. So it will continue on. It says that retained constraint is 66 because 0.1 times 663 is 66, and the constraint value are greater than EPS is 159. So the total is 225. 225. Okay, among those 225, the largest constraint occurs at constraint index 201, which is panel buckling constraint with this value, and this value must be greater than this value and less than that value, which does not satisfy the criterion. This number is greater than 2 times CT mean. So the ASTROS consider this is not a converged solution. And at the 26th iteration, you have 240 active constraint, and the objective function move limit and the design variable move limit are all satisfied, all less than 0.5%. And then at the 27th iteration, you find out the largest constraint is series panel buckling is 0.014, which is satisfied this criterion. Okay, therefore all constraints are satisfied. The optimization is converged. and then we punch out the optimized structure in the punch file. And in the baseline structure, all SQL4 are referred to the same PCOM car, but now each SQL4 refers to its own PCOM car, and because each PCOM car has a different thickness of each layer, and then it will print out the total thickness and what's the percentage thickness of each layer. And from here, you can see you will satisfy the decon-lam constraint. The decon-lam constraint requires each layer thickness must be at least 10% of the total thickness. So even in the input, everybody, all SQL4 refer to the same PCOM car, but the optimized structure, each SQL4 refers to its own PCOM car. And then we use VG.dat27 to plot the VG. And in the baseline structure, there's no flutter problem, but in the optimized structure, you can see there is a flutter mode which cross the zero damping line at 13,000 inch per second, which satisfies the flutter constraint. And the baseline structure is flutter free. However, the optimized structure treats the flutter margin for weight reduction. And then you can see the impact of buckling constraint. If with buckling constraint, this is without. So buckling constraint will increase the weight of the structure. And then you can display the strength constraint and the zero layer. The minimum is this number. The maximum is this number. Is all within this constraint, strength constraint for the zero layer, and likewise you can plot on other layer. Okay, and then you can display the thickness percentage of each layer. You can see all layer is about 10% of the total thickness, and because the minimum thickness is 0.005, and you can see all layer that the minimum thickness is above 0.005, and for the spot and rib, the minimum thickness is 0.04, which is they're all about 0.04. And finally, we can display the optimized spar and ribs and the skin. And you can see the skin thickness actually is not smooth. So the thickness distribution on the wing, skin, spar, and rib are not smooth. This is a typical issue of the element-based design variable approach, since each thickness is directly defined as a design variable, and no limit of the thickness ratio between adjacent elements is considered. For composite structure, this non-smooth thickness of thickness distribution can introduce sudden ply drop-off. This may give manufacturing problems, as well as a local resin-rich pocket that can induce delamination. For metal structure, the non-smooth thickness distribution may introduce stress concentration. A better approach is called Lagrange shape function design variable approach, will be presented in the next section, which can ensure the smoothness of the thickness distribution. Nevertheless, the element-based approach can produce a theoretically minimum weight solution based on which the structure designer can determine the region in the structure where the stiffness needs to be increased.